365 days in a year. The hours always go up, and there are 28 days in February, and there are 3,600 seconds in an hour, and there's 60 seconds in a minute, right? These are all wrong, all of them. Each one of these assumptions are incorrect because there's daylight savings time in leap years and leap seconds. So these are concepts that at least in America and some places all over the world, you deal with the concept that you make an assumption that there are 24 hours in a day, except that you have a developer, say in my current company, I got an email from a developer in India saying that they had an error processing an email that came in on the 8th of March of this year at 2:23 a.m. And I'm like, oh, that's a problem. Isn't that when daylight savings time in America started? And the answer is yes. And it's because it's spring ahead, fall back is, the current concept of what you talk about when you talk about daylight savings time is that, when you spring, you go from 2 a.m. to 3 a.m., you skip the entire hour of 2 a.m. And fall, you go backwards, so you actually get 2 a.m. again. So if you are dealing with some sort of an event system that cares about time, and you have something that has the time zone not specified, you can be dealing with a daylight savings time edge case that can cause your code to crash or can cause your library you're using to fail. What's even great about this slide is that there's some counties, not countries, but counties in America that don't obey daylight savings time. And that's just freaky. And daylight savings time is not 60 minutes everywhere. It could be 30 or 150. And the start and end dates actually change every single year. So there's a body of date time. I forgot the exact name of them, but they get together and they decide when daylight savings time starts and ends, and they work with Congress on it. And then we have leap years. And leap years are a problem because not every single calendar has leap years. And we talk about our traditional American Julian calendar. But if you're working internationally, you might run into other calendars that are used by local people, and they might not use a Julian calendar, and they might not even have leap years. Now, granted, most of ISO, which is the standard governing body, they use the standard of the Julian calendar, but not everyone does. And you could run into some rare cases where you might have something that's not right. All of these come down to having assumptions about how something works. And in programming, you care about those edge cases because those edge cases are when your application crashes or when your code that you write doesn't work in the way you expect. And all of a sudden something goes very bad. There was a bug in Lotus 123, which if you don't know what Lotus 123 is, it what was the first well-used spreadsheet application back in the business world in the 70s and 80s. Well, they had a bug where they treated 1900 as a leap year, but technically wasn't. And Microsoft Excel 2003 and earlier versions kept that bug so that Lotus 123 support worked as expected. And yes, that's just weird. But welcome to edge cases and how they can provide you with problems that can be solved sometimes in some pretty interesting ways. I did mention leap seconds. That's an actual thing that occurs. There have been 22nd, might actually be 28 now, might not have updated it, since 1972. And that means that if you parse data and you expect there to be seconds from 0 to 59, there's a 60th second. And so understand that libraries that you might use to do your date parsing might not understand this and might fail at times. This is a little slide from a website called XKCD where they talk about how to write traditionally correct numbers, because in Europe and America, we flip the month and days backwards. So we go day, month, year, and they go, or month, day, year, and they go day, month, year. So the ISO standard company or the ISO standard community have decided, well, these how we want to write numeric dates, which is month or year, month, day, from least significant to most significant. Now, here's something else about time you might have an assumption on. It's the same everywhere, right? I mean, it's always the same right here. And I'm not even going to count the fact that there's time zones. That's not going to, we're not going to talk about that right now. But the time continuum is always wrong. Time is linear. It always goes forward. It has no beginning or end. It never loops on itself. It's split into seconds, or maybe milliseconds, or microseconds, or picoseconds, or clock cycles. Time sucks. It's broken. It's not linear because of daylight savings time. And you can go and edit your calendar clock on your machine, and you can set the date to whatever you want. And all of a sudden, boom, now you've gone backwards in time according to the computer. There's something called the time epoch for Unix machines and all Unix drive machines, Macs, etc., that have this concept of an epoch because they only had so many memory to store the number of seconds for Unix time. So they started at the beginning of 1970, and that's their epoch start. In 64-base land, they fixed that problem, but in a 32-bit land, the epoch end was 2023. And for old computers, 2023 is actually another Y2K event, because that's going to be another time when systems will break down because time processing is going to go a little haywire. Time does loop upon itself because daylight savings time, you have another shift. And time is the same everywhere, on the same machine, maybe. This is some technicalities about the system clock. When you go into actually looking at how the system clock works on computers, the system clock is what keeps track of what it thinks the current time is. I'm not going to go into the depth of this one because this actually goes into talking about bare metal and the internals of a computer. So if you're doing any kernel work or any IoT work, you have to understand the system clock is always kind of strange because you can have drifts on the system clock. So let's have a quick lesson on time. A remote server runs a specific process at 11 a.m. that day. A developer at 10:57 a.m. went and edited that server to prevent that script from running at 11 a.m. But the problem was that the process had already started. And how did the process start? The process started because that machine actually was set to a little bit of a time difference than what the machines at the lab or at the developer's laptop had. So while we thought it was good and that it was running just fine, that machine was different and it had a completely different idea of what now was. And here's a pretty extreme response of a server with a particular time and a bunch of clients all reporting their own ideas of what time is. And so understand that as you make an assumption that everything is the exact same time, that's not true, especially when you deal with events. If you have event logging or if you take in events from an external system, you have to understand that there's going to be some sort of concept of external drift. The time is not the same. It's going to be different. And you're just going to have to deal with that drift. That's another reason why the last section talks about the network and the time it takes for the network to go on. So time is really difficult and time zones are really difficult, but I'm not going to talk about them now. Let's talk about something simple like email addresses. What's an email address? So this is a regular expression, which if you don't know what a regular expression is, it's a state engine to process and understand text. Now, the web is 99% text when you get down to it, because all HTML and all CSS and all JavaScript, they're all basically built from text strings. And so regular expressions are a great tool to analyze text and to pull that data out. So regular expressions are used by a lot of people to give you a great way to represent information. For instance, in this particular regular expression, in the very beginning, you can see that A-Z in lowercase a-z means all of the characters from A to Z in capital and all the lowercase characters from A to Z. The plus after it means one or more of those. So in this case, that A to Z would match an email in the matches that I have, because an email has all characters or all letters in it. And then has an @ sign, and then it has some extra information after that. But it doesn't match if you have a number in your email address. Because if you have a number in your email address, then this regular expression doesn't work. So let's add that. Let's add some more information. This regular expression gets much bigger. The takeaway is this is good, but it doesn't get all of them, because we've added concepts such as .company as a top level domain for a domain name. Like google.com could have google.company. So if you had that kind of email address, this would fail because it doesn't match .company. I'm not going to go into the technicalities of the regular expression. Just understand that the 2,5 and that last is kind of how big you want to match those characters are. And I've set this up that it only checks for anywhere between 2 and 5 characters. So now we've added some more things in there. This gets more and more complex as you realize that what you think is a simple thing, such as email addresses, is actually more complex. Now, that is a mess. And this is what has been defined as a near perfect regular expression for email addresses, but it's not even correct. It's good enough. This is a mess of insanity. That if you don't understand what it's doing, it's garbage. It looks just like a mess. And that's because when you make an assumption of something simple like email addresses, you realize that as you actually look at all those edge cases, it gets more and more complex. And so here is someone going, what? When you think it's something simple, you realize it's really complex. Email addresses are really, really, really difficult to parse. So your assumption that, oh, I can figure out an email address is actually, you could be right for 99.9% of the time, but then you'll run into ones where your assumption fails. Now I'm going to take a quick diversion and say this is a great reason why you use open source software and open source libraries, because a lot of the time, those libraries have done a good job at trying to find the edge cases and to provide you with a good basis to work from when you're thinking about things like time or email, when you have an assumption about something. Now, I will also say that you do need to vet your open source software libraries that you use. You do need to make sure that they're used by the community and that they have rigorous testing, because otherwise you'll run into the same problem of if you wrote this yourself and you didn't get a lot of edge cases in. Now let me look at the time, because time zones are a doozy. Let's talk about what time zones mean and why it's important to understand, because when you talk about date and time, you have to talk about time zones, because that's baked into the concept of what time is. Let's look at the US, where time zones have mostly linear borders and they follow country or county lines, and they're hourly based, and that they go north, and if you go north or south, you'll be in the same time zone, excepting the fact that there are some little, curves with counties in America. And locations don't change their time zones. They keep their time zone. You have a time zone until the end of whenever. Like you've always had a time zone, you're always going to keep that time zone. Here's another example of fallacies. Islands really mess up with time zones, because Kingston, Jamaica, and I need to shrink this down so I can see, and Easter Island, they share the same time zone, but they're technically miles apart because of the way that they cut the time zones. And they're not hourly based because India and Australia are famous for their 15 and 30-minute time zones. And going north or south generally keeps you in the same time zone. Well, I'll show you Australia. And counties and countries have changed their time zones for political or military responses. So you can't always assume that because a particular region in France has kept their time zone since the beginning of when time zones have been instituted, it's actually not correct. This is Australian time zones, and this is why I hate time zones. You notice when you look that there are these oddly hashed areas that are north and south of each other, and that's because they've got their bizarre time zones. And some of them are 15 minutes and 30 minutes off from the hour. Yeah, Australian time processing has always been a pain. It just goes to show you that when you make an assumption about something that you assume is simple, you really have to understand that there is a lot of complexity about it. And as developers, those complexities are what cause your system to fail. And that's where you take into account that even if you do the research on things, you might make mistakes. And so having a system that you write that understands that, yes, your system could fail, you need to then understand how to respond to those failures. For instance, if you can't parse a date time, what do? Does your system fail? Does it respond something to the user? Does it then assume that you're using the UTC time zone, which I didn't go into, but that's the universal time zone that is at the Greenwich Mean Time. GMT, if you've probably heard of, and UTC, they're the same thing. So I'm going pretty fast. I'm not really giving a lot of time for pausing, so I can talk about networking. But at this time, I'd like to know if anyone has any questions or if I should keep going.
I think it's good that you addressed the differences between the spring forward and fall back, because I know that that was a challenge with one of the applications that one of our agencies was working with, because, there were two, between the hours of I guess it's 2 and 3, you've
2
got,
a.m.
yeah, you've got two entries for the same time, whereas with their with the dispatch on when we spring forward, it's not as bad, because they had to do kind of an A/B thing when it came to the fallback. So I'm glad you addressed that.
Mm-hmm. So I'll go into a little bit more detail of you really need to think about, if your system fails, how does it fail? How do you handle a failure and how can you respond to it? Because as we write more and more complex systems, these systems need to understand how to fail gracefully and how to fail in a way where a human being can come through and reconcile the information. I don't talk about it here, but logging those kinds of failures and logging what the system thinks is the right thing is so important. Because if you don't have that kind of information, it's going to be really hard to restitch things back together. Now, imagine if you didn't just process American time zones, but you process all these crazy time zones from around the world. Now you're not talking about one time during the year where 1 hour shifts, but then you have to know what every single country does. And if you go back in time, they change that almost every year. So now you're talking about a horrible mess. How do you fix this? Well, you could not use times and you can use seconds from epoch, which is what internally computers tend to do. That's because date time math is just so complex. I'll pause for one more question, and then given that, I will go through the networking ones pretty quickly. And if there's no questions, then I will continue on to Networks. So the network is actually a really complex concept. I'm going to only talk about a few things, which is you basically generate a packet of data and you send it to someone else and they get that packet of data. That's how Zoom works. Zoom is basically taking all of our networking packets and they're basically taking that and redistributing to everyone else for like the audio and the video. That's how we can all see me talking, and you can see some of the other people on your screen because you're seeing the data coming in directly from their system and being sent out to you. Note that my data is now being basically duplicated and sent to everyone. So the network is actually a pretty complex concept. And there's been these assumptions about the network, that it's reliable and that its bandwidth is infinite, network's always secure, and that it doesn't change. I'm not going to go into the depths of these, but we're going to understand the beginning three, which is the network is always reliable and that it gets from point to point very quickly and the bandwidth is infinite. Because that's an assumption as developers we make when we're talking about talking to Apple or Google or to some server. It's like, oh yeah, we'll be there. I don't have to worry about it because it works on my machine. The bandwidth should be infinite. As developers, I always ask other developers, hey, what happens if the call that you're making, that API call or that network call, fails? Because everyone assumes when you go and call some API, say Google, that you're going to get your data back and it's usually going to be successful. Or if it isn't successful, then it will return some like 500 or known error code. But there's a lot of status codes that most people don't take into account that could be thrown by most modern APIs. Like if it's oversaturated, that API could throw back a 429 too many requests exception. And if you don't handle it, then you're going to have your code working for weeks or months or even years, and all of a sudden it fails for some reason. And that's because it got a status code that you never took into account. Understand that when you do talk on the network, you can have situations where it could just hang up or it could return with no information. And you need to be able to handle those. Whether it's gracefully giving some sort of error to an end user, or it's just sitting there and going, oops, something went wrong, can you try again? But you need to make sure that you understand and you handle those in a way that is at least sane. And when you talk about latency, which is how long it takes for data from me to get to the data from someone else, this little chart is a pretty good representation of the time it takes for information to move from one part of the computer or the network to another. So for instance, most of these are going to be talking about IoT concepts, but to go from San Francisco to New York without going through a satellite and going through basically the landlines, it takes about 40 milliseconds. And to go from San Francisco to Australia, it takes about 183 milliseconds. Now, this is an average, but when you go and look at how long it takes for a human to be able to be comfortable with the amount of communication that happens on a website, which is about anywhere 10 seconds or lower, is what people tend to accept. And it's even lower when you talk about responsive email or responsive websites, where you want to see things in just a few seconds. If you're in San Francisco and your client is in Australia, you have to take that 183 millisecond and assume that's one communication path. Now, if you're doing secure HTTP, that's 7 jumps to actually get the communication to establish. So multiply that by 7. And that's how long it takes just to get the handshake completed, much less get your data moving. And as developers, it's really easy to not worry about these things because, oh, on my laptop, it's fast. But it's not. It's actually fast for you. And you have to think about how your clients are experiencing your code, and their experience and the user experience gets so important. So you have to now worry about how long does it take to do a thing. Now, what's nice about the latency is zero slide that I have here on the right side, that's normalized to a second. And so when you look at things, it's like, oh, hey, if one CPU cycle, which is one clock cycle, which is how fast a relatively fast computer from when I wrote this happens, 0.3 nanoseconds, it's the equivalent of like 19 years to talk from San Francisco to Australia. And that's just kind of crazy, just how fast computers work. This is a great quote from Bill Gates, which is we have infinite bandwidth in a decade's time. And he said this on and off because it's an assumption that bandwidth won't be important. And bandwidth isn't important until it is. When you're using microservices and you're within your own data center, bandwidth becomes incredibly important. You want to optimize for as little data as possible so that you can get those hundreds or millions of calls coming into your API and you don't fall over. I've got a few more slides left. So I'm into some extra credit. So this is kind of describing how networking works at a core level, and this is really technical. So I'm going to stop at this point and see if anyone wants to go into the more technical stuff, or we can just open up for questions.
Dana, I'm glad personally that you called out the latency and the different times, because I feel like that's something I hear so much, like, oh, this worked really fast for me. And I never really know what I guess, the standard we're holding that up against. And so I'm always just like, I don't know. Or I hear, if I have a developer help me out with something and I tell them to come over, well, when we were still in the office, and I would have them, come to my desk and look at something, they always say like, man, your computer takes forever. And I'm like, does it really? I didn't think it was that slow. So it's just kind of funny to hear that, but then also see this, this chart of all of the different times and how they relate to each other.
So I'll seg that exact discussion into, it's good to have a diverse team. A diverse team can be everything from different hardware to different team members to different perspectives to people who might be colorblind or understand the concepts of colorblind design, because developers are famous for designing the worst user interfaces ever. And only in the last 10 years have we as an industry kind of woken up to not everyone is going to be using the system the way I'm using the system. And they've really embraced this idea of making the interface, making the way that something is used be as open as possible. And that has really driven both a lot of designs in user interface and also in the development the development world, because we strive for a diverse team and a diverse set of people to come and look at our designs from not just a front end, from also from a back end, to make sure that they can poke holes in it, they can get us the most functional system we can. Because ultimately this talk talks about how you have assumptions about the things that you write, and those assumptions can be wrong in a lot of edge cases. And then when you take that to extremes, those assumptions can be, is my user interface useful for someone? What happens if we have clients who are old or have visual impairments? Can they use the system? And in healthcare, which is the field I'm in, I deal with that very much, because I always have to ask other developers and product people and design to go, how can we make this good for anyone who might have visual impairments or visual problems such as color blindness? Those are all things that, as you look at a thing and make an assumption about it, you realize that you are actually being a little naive, and that adding people from different different steps of life and different backgrounds can help give you a environment where you can get the best software you can. And again, it doesn't even have to be developers. Like when you're using third-party software, those third-party softwares, those open source softwares, they're designed usually by a big team of people who are usually giving their time and energy to give you that library so that it has the most functionality it can. And they take their own assumptions and their own fallacies, and they come together and challenge each other to break down those fallacies. And I always encourage the developers that I work with to call out any fallacies and to challenge each other to make sure that we're doing the best that we can. Because it's really easy to make an assumption, have it be wrong, and then not have a way to recover from it. I'm gonna talk about how the network works at a kind of a base level, which is when I talked about those packets. Imagine a packet is an envelope. And an envelope has some information to get it to its destination. And this, I only have 2 slides for this. So after this, I'll be done with my talk. So let's postulate you wrote a book, you got a publisher, you negotiated your commission that had that book professionally proofread and sent back for adjustments multiple times, approved the final copy, received the first printing, the first edition, and you wanted to send that book to your frenemy who you dedicated that book to in the most annoying, cost-ineffective, and ridiculous way possible. So once per day, you tear out 1 page in order, of course, put it in a single envelope, as only the best envelope should contain a single page, address the envelope to the correct destination, and then mailed it, because you're a complete jerk and you hate book covers. That is a protocol called UDP, where you have an envelope with some information in it. Now, the problem with that information is it's actually inside the packet. Like you don't know what page it is, you just have an envelope with a destination. This is a protocol method when you're using, say you're watching Netflix. Netflix doesn't actually care about the order because it needs to get all that data in to process it. And so it doesn't need that information on the packet. It just gets all that data in, opens all that up and goes, oh, hey, this is page 7. And it goes here. That's why you get some weird artifacting on Netflix and YouTube. It's because they didn't have all the data and they're using an algorithm to give you that data in an extrapolated way. Now, let's assume you want to be less of a complete jerk. So you decide to put the correct page number and a count of the number of vowels on the outside of the envelope, just to provide some sort of verification of which page it's supposed to be on the inside of the envelope and to make sure it's kind of correct. You still send only one envelope per day, but by registered mail this time, so you actually know it got to the destination. And you enjoy being a complete jerk and broke because registered mail isn't cheap. That's TCP or the other protocol. The difference between UDP and TCP is that TCP has information on the envelope that says, by the way, this is this page number, and this is the way to verify the data in here is great. An example of TCP is when you're sending data over the network that you need to validate is correct. The example would be a web page. A web page is sent over TCP because you can't get the order of the data wrong, and you have to verify that you got all of the data correct. Otherwise, you're not going to give them a complete page. So TCP comes with extra information on the envelope to have the system analyze it and go, oh, hey, this is correct. The data inside of the envelope matches what's supposed to be on the envelope. And then if you don't get one of the letter or one of the envelopes, it came in through registered mail. So you have a way to find out where it is. And in this case, you, as the caller, you would send back to the person sending that data going, oh, hey, I need envelope 7 because envelope 7 never got to me. And then they'll resend envelope 7. Because because you have a list of every single number or every single page number on each envelope. You also know if the data is incorrect because you have a way to validate the data via either a checksum or some other external method. So when you compare the data inside the envelope to what the envelope says it should have, you have some sort of way of validating it. That's my talk. I covered this really quickly. This is one of the big topics that I really like to talk about, which is fallacies, and assumptions. The assumptions of development is what makes someone really challenge their own ways of coding and to find ways of their craft and their art to be as good as it can. And I really hope that you are in an environment when you work with other developers where you can challenge each other, where you can push them to make sure that they're doing the best that they can, and that you have an environment that supports that. Because we all want to grow and learn, and in doing so, you want to have an environment that is as open and stress-free as possible where you can bring those things together. So now I'm going to open up for questions. Thank you very much.
Hey, Dana, I have a question. How can we start the conversation with the developers we work with so that we start challenging them to think about all of these things that, like you said, that we assume are so easy but really aren't? Like, how can we start to begin that conversation if we're not developers ourselves, and just get them to that spot where they're thinking of these things?
So what I've tend to do is I bring the example of dates and time to everyone. That includes product, that includes non-developers, to talk to them about how we have in the development world assumptions that can be ultimately false. It resonates with everyone that I've ever talked to because time and date are a fundamental concept that everyone understands, but then they don't understand about things like the leap second. And when you talk to them about, well, there's this concept, did you know that this exists? And the way to phrase it is, it's not about me being smarter than you. It's a way to understand that I have a different perspective on things, and maybe this will bring us to a better conclusion. It will bring us to a product that is the best it can be. Because when you extrapolate that back out into any other conversation, this isn't a fight about who's smartest. This isn't a fight about who has the most knowledge. This has the approach that I want someone to give me a different perspective so that we can figure out if we can work together so that it benefits everyone. That's the easiest way I've ever used to talk about this from a perspective of a non-developer. And from a developer point of view, there's all kinds of things you can have assumptions on. Like you can even use date and time or email parsing, and there's tons and tons of other ones that you can come up with.
Thanks. I have to say that I'm curious to have this conversation with some of the developers I work with, because I know that we track gifts, and we have international customers, and we do have dates and times where we track when those gifts came through. So now I'm curious what is in place or what they have in place to handle all of that. So I'm kind of curious now knowing this, how we're keeping track of that.
Now, usually the library that they're using will handle most of it. They'll handle 99.999% of the cases. I've seen a lot of Java libraries, for instance, that don't handle leap seconds and they just fall over. And it's just a thing. So yeah, it does come down to what libraries you use. It also comes down to the approach of where can we have a problem? Like, we're making these assumptions, where are these assumptions incorrect, and do we have a proper way of handling them well? Now, I will say that logging and other tools and gracefully failing are ways that these edge cases can be mitigated.
Dana, I have a question. How do you document what your assumptions are when you're going in and working on a project or in your code, so that future you or future coworker can know what some of these things are?
That's a really good question, because at Athena, when we go into larger projects, we do talk about the assumptions, and we split them into three things. the knowns, the known unknowns, i.e. things we understand we don't know about, and then the unknown unknowns, which are things that we could postulate we don't know about, or that we know we specifically have no idea how it works. An example of a known would be any known assumptions about the data we're getting in. We know it looks like this, but we don't know all the edge cases. And a known unknown would be an environment where you know it exists, but you don't necessarily understand what that data could send you, but you know that you're getting data from the system, but you just don't understand it yet. And then documenting an unknown unknown would be, well, we have no idea where their system runs from, so we don't know what the latency is going to be. Or we don't know what happens when the data comes in and it's failing. We don't know what data it could return to us. It's good. It's all about documentation. It's all about leaving a trail for the other developers and to actually write this stuff down and get it documented. Because without it, it just gets lost. Any other questions? It is 12:47, and I believe there is some other information that wants to be provided to us.
I have one final question. What other resources would you recommend people go to if they want to explore this subject more? Books, websites, YouTube videos, anything like that?
Developer fallacies is actually a pretty big concept. And just going to your favorite search engine and typing in developer fallacies will give you a lot of very good resources. So this is not a topic that is unknown. It's just not a topic well discussed.
Thank you.
Well, thank you all.
I will share my screen real quick so you can wrap us up, Emmy, and to Dana's point, call out what's coming up next.
Thank you.
And here we go. Oh, oops. Present is what I want.
All right. Again, I want to thank everybody for coming today. Hope you've enjoyed the talk. And looks like we're going to have a little bit more time. So if we have a few more questions, we can follow up with them. But we did want to remind you about the event we have next week, August 19th. It's from 5:30 to 7:30. We're scooching these times in a little bit since we don't have commute times. One of the bonuses of everybody working from home. And this Wednesday event, August 19th, is the What About Getting Results Today. It is going to be a discussion about how to move yourself forward. If you have any questions about membership, you can certainly email membership@awtaustin.org. Membership is only $60 a year. While we're doing virtual events, most of our virtual events will be free for members and low cost for non-members. So you will easily earn your membership back this year in events like that. We are also expanding our programming to 2 events per month. We're trying to do a daytime event and an evening event so that we can support whatever work schedule works for individuals. We have an individual or a team Slack channel for AWT where we have a jobs board and we have an applause board and information like that on there that is exclusive to members. So if you have any questions, feel free to reach out to membership@awtaustin.org or Heather on Slack if you're a member already and you have any additional questions about membership. And sorry I'm a little behind. My computer crashed at the beginning of this. I'm doing this off of my phone now. Am I supposed to announce Boss Ladies here too?
I think you can if you
Okay, well, I certainly want to because I certainly want to give recognition to Ms. Denise Pena who is one of our newest boss ladies. She is one of our August members for Boss Ladies. She has joined us as a volunteer recently, and she is coming on strong, and she is helping us out. Cannot be grateful enough that you are running the Zoom today, since I had so many technical difficulties. Can't imagine what this event would have been like had you not been running the show today. So I want to thank you. And then for any of those who joined our July diversity and inclusion event, Tahar Rao Martinez is our other August boss lady, and I just want to give a big round of applause to both of you for all the work you've done to support this organization.
Demi?
Did I cover everything?
I think that's it.
Do we have any final questions for Dana? Did anybody come up with anything, or are there any in the chat? I can't see the chat on my phone.
I'm not seeing anything in the chat.
Okay, well, for anybody who doesn't know, Dana is a member of AWT. And so if you have any further questions, you can hit him up on Slack and he will help you out. All right, I guess we're gonna give everybody a whole 9 minutes back. You can go grab a sandwich in 9 minutes before your 1 o'clock meeting like me. Thanks everybody, have a great day.